Hello, everybody, and let's get started. Welcome to the session called R and Spark as yin and yang of scalable machine learning in Azure HD Insight. I'm Maxim Lukyanov. I'm program manager on big data team in Microsoft. I work specifically on R server and Spark in Azure HD Insight service. This is going to be a dense session, so feel free to ask your questions as we go. I'll try to answer them. And we'll also have 5 minutes of Q&A in the end. And I'll stick around, so if you have more questions, I'll be happy to answer them after this session as well. In this session, we are going to talk about R server and Spark. We'll cover core capabilities of these products, but the focus of the session will be on the combination of these two, of how R server can be combined with Spark to achieve a variety of scenarios of data analysis, starting from data preparation, data exploration, data transformation, and going into feature extraction and data modeling. And that could be data modeling in R or Python in the language of your choice. We'll also include and we'll go a little beyond the capabilities, out-of-the-box capabilities of this product, and we'll talk how you can tap into ecosystem that is formed around R and Python and bring some library, for example, a deep learning library, into a solution to achieve the goal of your project. So let's get started. So if you're in this session, you probably or likely know what yin and yang is. But just in case you don't know, let's cover this topic as well. So yin and yang is an ancient Chinese philosophy which dates back to Daoism, and it actually predates Confucianism. In the core of the yin and yang is the idea of balance and duality. Yin and yang sees the world as a set of opposing forces that seemingly locked in the conflict, but under more close inspection reveals their interconnected and interdependent nature, where one force gives rise to another and they actually coexist in harmony. When we talk to our customers, we frequently have questions. That's quite a common question where customers ask, hey, the Spark has machine learning library and our language is all about machine learning. So which one should I use? Which one do I choose? And this creates this perception of a conflict. We need to choose one or another. They compete for our attention. So in this session, we'll try to resolve this conflict and show how R server design actually combines strengths of R and Spark, how it brings distributed compute engine from Spark and combines it with the popularity of the statistical language such as R to deliver some compelling and flexible product. So let's get started. So we'll start with kind of a setting the stage, the context of what we are going to talk about in this talk. In Azure services, we have a set of services that are dedicated for processing of big data and doing variety of machine learning tasks. This set of services are combined under the umbrella of Cortana Intelligence Suite. Within this Cortana Intelligence Suite, we will talk about one specific service, which is HD Insight, that provides capabilities of scalable machine learning. With the help of HD Insight, you can create clusters of multiple machines with R server and Spark running on them to solve your machine learning problems at scale. So that's the focus of this talk. But even if we narrow our focus into this scalable machine learning or machine learning over big data, if you wish, the landscape of all of the things you can do in machine learning is infinite. So let's start with classifying what machine learning algorithms we are talking about. I assume many of you are data scientists here. Actually, let's do a show of hands. How many of you consider themselves data scientists? About half of you. So you probably know really well the classical or academical classification of machine learning algorithms: supervised, unsupervised learning, variety of classifications like that. But in this classification, we'll go from the different point of view. We'll talk about machine learning algorithms from the point of view of the users, of the businesses that pay for these algorithms or incorporate them in their business, in their products. From that criteria, with that criteria in mind, we can divide machine learning into traditional, specialized, and deep learning algorithms. And traditional algorithms talk about the most commonly used algorithms, primarily around predictive analytics, hypothesis testing, some classification, some clusterization. And those algorithms are used in kind of nearly every place where you see statistical machine learning methods involved. Specialized algorithms are less commonly used, but they have achieved a de facto status in some vertical or industry as a solution to a particular problem. For example, PageRank, collaborative filtering, and PCA are examples of such algorithms that are well known and used very frequently. And finally, deep learning is categorized as a separate thing because it drives in the recent years quite broad new applications. It drives our rethinking of what is possible with machine learning and even artificial intelligence in general. So there are many new applications that this category of algorithms drives. So going with that categorization, we can now talk about use cases, how or what is possible with R server and Spark that we are going to talk about. So in the category of traditional algorithms, by definition, those algorithms that are used almost everywhere. So we are talking about traditional enterprises, very large enterprises. You can say our brick and mortar enterprises that used statistical methods for decades now. So you can find these traditional algorithms employed there very broadly. And an example of that would be actuarians in some financial services, assessing risks and determining rates for our loans. So that's a very well-known kind of application of machine learning. If you go into specialized algorithms, then it would represent kind of activities in both traditional businesses, but also in quite a broad selection of new web businesses. And good examples here would be our search algorithms that we employ now on the web very broadly. If you go to Amazon.com or any other retailer, you would find yourself facing some product recommendation algorithms that recommends you products or services. And all of those are driven by well-known and frequently customized algorithms that we categorize as specialized algorithms. And finally, in the deep learning, we are moving in towards kind of a more bleeding edge type of applications of the algorithms where we have a very wide variety of startups that are vying for our attention, and also traditional enterprises that are building new products and capabilities in their respective industries. All of those capabilities and use cases are possible within the boundaries of these two products in Edge Insight service. We have two categories of cluster types that you can create. You can create just vanilla Spark cluster, and you can also create what we call premium offering that includes R server capabilities on top of Spark clusters as well. So let's talk about those two offerings and how they interact with each other. So let's start with R server. So first, what is R? Like half of you are data scientists, so you are quite familiar with that. But to summarize it quickly, R is a very popular programming language employed for statistical needs. It was invented by statisticians, and it has accomplished quite great success in that area. It becoming almost a de facto standard in institutions when people study statistics, and it has created an ecosystem or a community around R language that has produced or solved a variety of statistical and machine learning tasks that are available on CRAN as a variety of machine learning packages that you can easily use in your R solution. So it is quite successful. And the Spectrum rating actually shows that its rise in popularity of the R language is quite tremendous. It shows R on the 5th position in the overall language ranking. It's even hard to believe, but that's great. Despite its popularity, R is not a perfect language, and one of the few kind of top problems with R are as follows. The first, it traditionally was designed around single-threaded operation, so all of the open source R routines assume that they operate on a single thread, and also assume that all of the data that you're operating on resides in operating memory. So those two restrictions hardly limit how far you can scale your R solutions in terms of data sizes. And finally, there are built-in data frame libraries in open source R that are quite inefficient when they deal with larger, not even large, but just larger data sets. Moving or creating data frames is notoriously slow. And finally, it's not enterprise ready. It's open source R, so there is no SLAs you can get for it. So R Server, that's an offering that Microsoft created after acquiring Revolution Analytics, aims to solve these problems. So first, it brings a fully compatible with open source R solution that also can scale quite transparently beyond the limits of the single machine or single thread. So it's multi-threaded, and it also can scale out into even clusters of machines. So it solves the scalability problem. It also allows you to fairly easily distribute your arbitrary algorithms, as long as you can just run them in parallel or parallelize these algorithms. And finally, it gives enterprises the critical criteria that they are looking for, which is product support, stability of the released builds, and SLAs if you're talking about cloud services. So that's a value proposition of R. So let's take a look at how R Server looks like, how you achieve all of the scalability promises that R Server have. So if you start with open source R, then the simple program that would build some logistic regression would look something like that. You would read the data, and then you would run machine learning algorithm to build a model around this data. So in order to switch to a larger data set that doesn't fit into memory, or to run this learning algorithm faster, with R Server, all you need to do is to just switch function names. So instead of reading the data by out-of-the-box functions, you would use R Server function to do this. And instead of regular linear model algorithms, you would use Rx logit function that R Server provides. And once you do this, R Server behind the scenes will actually distribute this algorithm and run it on whatever hardware you have. By default, it uses a notion of compute context to specify how you want to run this algorithm. And by default, the compute context is set to a local compute context, which means it would run your machine learning algorithm on a single machine, but it will use already at that point multiple cores of your machine. But it's as easy to switch to a cluster or distributed computation by setting compute context to something other than local context. In this example, it shows how you can create a Spark context that would capture configuration of your Spark cluster. And once you set your compute context to a Spark compute context, behind the scenes, all of the computations now will happen in parallel on multiple machines in the Spark cluster. So from the R user point of view, you actually don't need to understand how Spark works. You just tell R Server to, hey, go distribute over Spark, and everything else is done for you by R Server distribution algorithms. On HDN side, when you provision this cluster, R Server cluster, what you get is a set of data nodes that actually will perform the computation, and also head nodes that kind of manage the cluster, and an edge node. And the edge node is where your R Server kind of launches, and you can connect your preferred development environment to this edge node and run your R scripts on it. So if you run on the local compute context, then your R program will run only on the edge node using whatever number of cores this edge node has. If you switch to a Spark context, then transparently your program will run on all of the data nodes in the cluster, and will to do that, it will use Spark as a distribution framework, but on each node, it will actually call back into our server routine to process the data that Spark delegated to that particular data node. If we look closely at what happens during the computation, we'll see that not only the R server capabilities are available on this cluster, but also Spark capabilities of the cluster. So if you look at the edge node, we can see that, hey, it runs R server and deploy R. That's R server capabilities. And you can connect your development environment, for example, R Studio or R tools for Visual Studio to this edge node to run your R programs. But at the same time, there is a variety of capabilities that Spark cluster, the same cluster, exposes. For example, you can run Jupyter notebooks to run your Spark scripts that do ETL on your big data asset. Or you can run your development environment for Scala and connect it to a Spark cluster as well. And even you can use your Spark cluster as a data warehouse and connect BI tools like Power BI or Tableau to this cluster and expose the data sets and artifacts that are available to this cluster in the form of a dashboard. And the best part of that is you can combine these two capabilities and use them on the same data sets and combine BI tools and machine learning capabilities of R at the same time. The way this R server capabilities and Spark capabilities interact with each other is through resource sharing. And by virtue of using Yarn as a resource manager, we achieve ability to share resources between the two workloads. So once you launch the R server program, behind the scenes, it will actually create a Yarn application that will run inside of it Spark code. And this Yarn application will dynamically request appropriate amount of resources from your cluster. At the same time, you can run Spark program, and which will create another Spark application, and they will share resources of the clusters that way. So when you run your R program in a distributed mode, what do you get? How much speed up does it provide? Can you go to like infinite amount of data? Well, the actual number that we got by doing some benchmarking exercises actually says that pretty much yes. So once you use distributed framework such as R server, you are no longer limited in terms of your data sizes. We tested in this example up to billions of rows on a 100 node cluster, and we got almost linear scale across these data sizes. For example, if you run such a data set on open source R, it will crash at around 25 million rows. We also compared to various computation modes that are available into R server. So if you use, in this example, we used 5-node cluster, 5-node Spark cluster. So if you use 5-node cluster, it would be approximately 36 times faster than using a single machine, using even a local mode of the R server. And you can see that if the data set is reduced in size, then the relative gain in terms of speed is reduced because there is additional overhead associated with Spark context when you need to first create a Spark application before you can run computation on it. So the larger the data set, the more becomes the gains in terms of relative numbers. And the second chart talks about the original kind of MapReduce way of distributing computation. Our server supports both of them at the moment, so you can use MapReduce as a way to distribute computations, as well as Spark as a new computation engine. And we'll talk about Spark in a bit more. But this chart shows you that this latest and greatest compute engine that is provided by Spark is certainly much faster than the old one provided by MapReduce. So there is no reason for you to kind of consider the old ones. You can safely go and use the Spark. And finally, to conclude our very brief overview of our server, here is a list of algorithms that it provides. So this is a list of algorithms that natively have distributed implementation. So as shown in the example, you can just write your R program, and behind the scenes, our server will do the distribution for you. If you compare this list to the categorization of the algorithms that we did, this maps very well with our notion of traditional algorithms. So you see predictive statistics here, hypothesis testing, clustering, and one important function to call out here is Rx exec function. So that's a universal function that allows you to parallelize execution of arbitrary R script. That is a very powerful function when you are talking about some algorithms that is not covered by this list of out-of-the-box parallel algorithms that allows you to bring in some novel algorithm from our ecosystem and in some ways simply run it in parallel on the distributed data set. If you have more questions or interest in R, we have a couple of other sessions that go in a little bit more detail on our server, and I list them on the farther in the slide deck. So you're welcome to attend those sessions as well. Okay, so let's talk about Spark and how it interacts with our server. So Apache Spark is one of the kind of hot new things in the big data space. In a couple of years, it's basically took over the mind share in the big data industry and now has support from all the major vendors that provide big data solutions. And every startup and company has incorporated Spark in their pitch decks and products. So it has great momentum, and it has very good community support around it as well. One of the traits of Spark that kind of drove its popularity is its approach to how it provides its capabilities. It has a very nice structured architecture where it provides platform capabilities at Spark core level that are very easy to utilize at the higher levels to build kind of workloads that uses distributed compute engine to implement more application-specific functionality. For example, Spark SQL shares the same distributed compute engine that Spark provides with Spark Streaming, which is a real-time event streaming processing engine, as well as with GraphX, which is a library for graph computations. And machine learning library as well uses core Spark computation capabilities to perform some machine learning algorithms, to implement some machine learning algorithms. So from that point of view, Spark provides a platform for distributed computations. And our server is one of those workloads that uses Spark platform to distribute its computation. So from this slide, it's fairly obvious that our server sits side by side with machine learning library, and the question arises, hey, how they compare with each other, and do they compete, and which one should we choose? So let's dive into this question a little bit more deeply. So if you look at Spark ML algorithms, despite the slightly different groups of the algorithms, they basically translate to the same set of traditional algorithms that we talked about before. And that clearly sets them at odds with capabilities that our server provides. But Spark is not only available in kind of R language. Spark is actually native to a Java language and to a Scala language. So, and it also has bindings in Python language as well. So Spark, as a computation framework, is actually multilingual. So if you look at the different language bindings of Spark, the picture kind of changes. So these checkboxes compare what is available in our server as compared to the to Spark machine learning library. So there is pretty much parity between the two. But if you look at the Spark R bindings, then you will find that they are very lacking. At least at this point, Spark only kind of has started to provide any meaningful bindings of the machine learning algorithms for the R language. But if you look at Python language, then you'll see that Spark actually kind of focusing itself on the Python language as a primary way to provide machine learning capabilities in Spark ML lib. So that kind of immediately removes any conflict whatsoever from the previous picture, because at least at this point in time, Spark machine learning library is mostly available in Python, and that kind of resolves its conflict with the R server. But that's also good, because if you look at data science landscape, there are actually two dominant languages in here. R and Python are the most popular languages. And I found this poll on the Knuggets website that compares popularity of languages in the data science community. And according to that, R is the most popular one, followed by the Python, and the Java is a distant third. So according to that slide, we are basically talking about that between R server and Spark machine learning library, we have coverage for two most popular programming languages for the data science community. And that leads us to our kind of a first conclusion of this talk, is that R and Spark complement each other very nicely from the language coverage point of view. You get premium experience in R server for the R language, and you get good experience in Python language from the SparkML library. As well as we discussed, there is a synergy between these two products, where R server uses Spark to distribute its computation, where Spark in the end calls back into R server to execute some R code. Okay, so with that, we can take a look at how it looks in practice. Do you have any questions so far? Yeah, one question on the back. Sorry, I cannot hear you from here. Can you go to the mic?
So you talked about open source R, but what about the R support that's been in Spark since 1.5, I think? Is this an extension of that, or is it different? Can you compare?
I see. So so the question, well, I don't need to repeat your question because you used the mic. So what we compared here is R server capabilities, which is certainly extension on top of open source R, with the capabilities that Spark provides in its R language mappings. So it's a Spark R library that is available in R that provides you access to the Spark machine learning library capabilities. So from that point of view, Spark R library actually doesn't have much in terms of machine learning algorithm support. It's mostly focusing on the data transformation capabilities of kind of core capabilities of Spark.
Right.
Okay.
Thanks.
Thank you. So one more question, and we'll need to go into demos. But we'll have Q&A in the end.
Hello. How scalable is that SVD implementation you mentioned? Because it's not in R, right?
Well, I cannot comment on the SVD implementation. So SVD implementation comes from the Spark machine learning library. We haven't benchmarked this particular one, so you would need to try on your own to see how scalable it is. But all of the algorithms in SparkML library actually use Spark distribution engine. So from the point of view of what is the maximum data size that you can handle, that shouldn't be a problem. But the performance of the implementation, that may be a question to ask.
And nowadays you don't have any in parallel R, SVD implementation?
Sorry, parallel R, SVD implementation in parallel R?
Yeah, I mean, you showed some kind of native algorithms and
oh, you mean R server?
Yeah.
Yeah, as far as I know, R server doesn't have SVD implementation.
Okay.
Okay, let's proceed to the demo. So to give you context of all of these Azure services, because I know there are sometimes too many of them, and it's hard to keep track of them. So what you see, at least what you should see, is an Azure portal. And on the left side, we have a list of all of the services that is available in Azure. So with HD Insight, you'd click on the HD Insight cluster services, and you can see all of the existing clusters in the list, but you can also create a new one by clicking an Add button. So that's the power of Azure Cloud, where with just few clicks, you can go and create, for example, a whole cluster of machines configured to run R server or Spark. So here you would specify parameters of your cluster. So you can say my demo cluster as a name of the cluster, and in the cluster type, that would be a first thing where you can select what type of cluster you want. You can select vanilla Spark cluster, and then you can upgrade your vanilla Spark cluster to a premium cluster that would include Microsoft R server on it. So we won't go through the steps of creating actually a cluster, because that takes time and we have very limited time. So I have pre-created a cluster already. And once you have your cluster, it comes with all of the Spark services like Jupyter Notebooks and BI capabilities, as well as you can install R server friendly RStudio development environment. So let's jump into this cluster with a pre-created that I pre-created for this demo. So what you're looking at is a sample Jupyter Notebook that represents capabilities that you get from Spark. And in this Jupyter Notebook, you basically at a very high level, to describe what notebooks are, you can combine descriptions about what you're doing in this notebook with the actual code. So you can see that I have a description that says, hey, this step will load data. And then I have a cell that has some Python code in it. And this is a Spark Python code that allows me to do some basic data exploration and data manipulation steps and data transformation steps. So in this example, you can see that I'm reading some text data from a location that has a prefix ADL. That location designates Azure Data Lake as my data source. So in this scenario, we're talking about, hey, I have some random set of data, or I put some random set of data into my data lake, and now I want to explore it and go forward towards building some model out of this data. So this data set in the data lake is very easy for me to explore using Spark because it's an interactive compute engine. So I can just execute this cell by using Shift-Enter, and immediately I can see kind of a top 10 lines of this data set. And in these 10 lines, I can see that, oh, this is something like a JSON data set. Fortunately for me, Spark has a built-in support for JSON, so I can easily read this JSON file and convert it into a table. So table in Spark is like just this regular SQL tables, which I can then query. So I'll skip this step that loads the data as a table. The key step here is that once I read this data frame from this JSON data, I can register it under as a table with the name flight. Then Spark as an in-memory computation engine gives me great power in terms of speed with which I can process this data. I can cache this table in memory using this command, cache table. And since from that moment on, I can really quickly work with a full data set and kind of analyze and slice and dice this data set. For example, let's start from counting just a number of rows in this data set. So in this one, we have 160 millions of rows, but because the data set is cached and I'm using Spark, I can work with it in an interactive mode. For example, if I want to scan this whole set of data and aggregate it in this form, so this is an airline data set. Probably you will see this type of data set in demos quite frequently. It captures arrivals and departures of the airplanes. And in this query, we are counting kind of average delay grouped by date of the week. So we are processing 160 million of rows, and you saw that because of the caching in Spark, there's a 10-node cluster, we were able to get results in the matter of seconds. So in a few seconds, we get the results, and in these Jupyter notebooks, we have nice automatic visualizations capabilities that you can use to quickly explore your data. So on X, let's put day of the week, and on Y, we'll put the delay. So, and with that, we get a chart that shows, let me scroll a little bit. That shows that on different days of the week, and the number here, I didn't decode it, represents a Monday is as 1 and Saturday as 6. It represents that average delay was changing this way across the days of the week. So that assumes that on Friday, it's the worst time to fly, and on Saturday, it's the best time to fly. So once I kind of explored my data and started to have a sense of it, I can convert it, clean it up, and convert it into a data set that I can use for my machine learning tasks. And we won't do the conversion step. Let me make it a little smaller. But the conversion step would look like something like I will select a specific set of columns that I care about. I maybe may apply some filtering, some feature transformation even maybe, and write it down as a new data set that I will later on use for my machine learning model building. So let's switch to the RStudio. And the nice part about this setup is the same cluster has both R Server Studio and Spark capabilities. So I can quickly switch to RStudio and run now my R code that will operate on the same data set that I prepared in Spark. Can you see it? Can you see this code, or do I need to zoom in? No? I see nodes. OK, so we'll keep it that way. So in this data set, again, you can see that I'm reading this data from data lake. I'm reading this data set that we just described. And then I'm building some factors and features that represent the same problems that we just solved in Spark, which represents weeks and delay times. So let's execute this code. And this part of this R script represents, demonstrates how you actually create a Spark computation context. You basically, because it's a R server that runs on Spark cluster, basically all of the parameters of the Spark cluster are known by default. You just need to create Spark context and specify which name node you need to use. So once you set the Spark as a compute context, we can run this linear model first training that would solve the same problems that we just solved in Spark. It will basically build a linear model represents average delay time based on the day of the week. So Spark now, R server now started to talk to Spark cluster to start training this model on this data set. And we can observe that in the Yarn resource manager. So on the same cluster, on the head node, we have Yarn resource manager that kind of governs all of the resources available on the cluster. And you can see on this screen various Yarn applications that are running. For example, remote Spark magic here represents the Spark notebooks that we were running in the previous step. And if I refresh this page, I can see that new application was created here called Spark R. So that's a Yarn application that Spark has created and uses Spark as a distribution engine to execute our computation on the cluster. So now if you go back to RStudio, we can start seeing that the progress of computation as each of the distributed tasks being executed, it reports back about its progress. So the way this kind of interaction works is our server basically asks Spark to divide this large data set into into chunks called partitions. And then each partition of the data set, Spark starts to process on each particular data node. And once this processing starts, Spark then calls back into our server and gives each partition to actually do some machine learning tasks on it. And our server picks up from this point on and actually builds the model. So now that the process completed, this stop, we can see that the Yarn application is now disappeared and the computation is complete. So let's see quickly what we can do with that. We can display summary statistics on this model that we just built. And we can also use some R plotting mechanisms to plot this. So let's first plot the delay time, and that, as it should be, represents exactly the same chart that we get from Spark. It basically represents simply an average delay based on the day of the week. And we can also plot counts, number of data points in each sample that would suggest actually why the airline delay, arrival delay is lower on the Saturday. Well, this chart suggests that just simply because there is way less number of flights on the Saturday, that may be an explanation of why the arrival delay is lower. There is also regression models that we can build. So in interest of time, let's skip that. Actually, I think I already ran this model, so let's try to actually use it. So after we have built the model, the powerful kind of thing about our server is that you can switch back and forth between computation contexts. So you can switch back to a local computation context, as I'm doing here, to run some very quick local computations on the model that was built on the cluster. So in this case, we can start predicting locally without the use of the cluster, and that executes fairly quickly. For example, in this case, we were predicting what would be the arrival delay between different, depending on the origin of your airport. So if you were flying from the Seattle, the probability of the delay in your arrival of more than 15 minutes would be around 30%. But if you're flying from Atlanta, it would be higher. So we are not in the best position from that point of view. But we are still better than New York. If you were flying from JFK, you would have much higher probability of the delay. Okay. So that gives us kind of a basic things that you can do with our server and Spark together. So let's move forward. So the next topic, the kind of an extra topic that I have for this talk was how you can bring kind of external libraries to run on this distributed computation framework that we have, platform. From the keynote, you already got a pretty good introduction into deep learning libraries. So I will go very quickly over this. Deep learning is important because, again, it kind of changes the way changes the notion of what is possible with data science. So it's quite expected that it would be a point of interest for us in our new project. So how we can use it in HDInsight, our server, and Spark clusters. So one of the properties of deep learning is that it actually depends on the massive amounts of training data to be available. And the computation models that it uses are actually very computationally extensive. So this combination of these two big things, big compute with big data, actually require you to use very large computation resources. This is an example of one of the newer deep learning models. It was actually designed with the intent to make it computationally efficient. And the result of that efforts was a deep learning model that has 25 million parameters. It takes 2 weeks to train this model on 8 NVIDIA K80 GPUs. So 2 weeks on on this kind of massive amount of compute. It's a great example of the image recognition deep learning library. It can differentiate between spotted salamanders and fire salamanders. So that's great. But the point of this slide is that it requires massive amounts of compute. And that means that in Azure Cloud, we have very good candidate for solution to this problem, where we have both clusters of VMs, and now we have GPU-enabled VMs available as well. So at this point, we are talking about a little bit about the future of the computation in the cloud, because GPU-enabled VMs are not yet available on the HG Insight clusters, but the open nature of the Spark ecosystem and distributed capabilities that Spark provides makes it very kind of easy to utilize these libraries inside of your HG Insight cluster. So across a variety of deep learning libraries that are out there, Tiana, Torch, Kafka, and things like that, there is some of them that support Spark as a native distribution engine. And that one is a deep learning for J, and there are others as well. In this talk, we actually won't probably have time for demo, but we'll have a slide on how you can easily run this deep learning for J library to train your deep learning model. On other talks in this summit, you can actually also have, if you're interested, you can learn more about CNTK library and MXNet library. We have 2 sessions dedicated to those libraries as well. But in terms of using Spark as a computation engine for deep learning, it actually looks pretty simple. So on this slide, you see the commands that you would need to use in order to run this deep learning library on the HG Insight cluster. So you just install Maven and Git, and then you would just clone the example from this deep learning for J GitHub, and then you would use a Spark submit to submit this Java-based program to the cluster, and it would just run. That's the power of using kind of open frameworks for computation. Okay, so at this point we can put all of these pieces that I talked about together and have a final landscape of the scalable machine learning offerings that is available in HG Insight. So for traditional algorithms, certainly within the R language landscape, R server provides premium experience to run your machine learning algorithm at scale. Spark, on the other hand, with its ML library, complements this offering in the Python language. And when we are talking about more specialized algorithms, something that is not available out of the box, certainly capabilities of R server to parallelize arbitrary R code and similar capabilities in Spark to parallelize arbitrary Python code gives you access to the ecosystem of the machine learning algorithms available in the wild, and you can bring them according to your needs. And finally, for deep learning algorithms, with the advent with the arrival of the GPU-enabled virtual machines, Spark provides very simple to use platform to run these algorithms as well. Okay, so let's recap. We talked about the R server and Spark and how you can use them together to basically combine capabilities of the Spark as a distribution compute engine and popularity of R language together to build something that is greater than the sum of the parts. And that is kind of a modern but still canonical example of the yin and yang, where you have 2 opposing things that contribute to each other, contribute to the success of each other. In terms of related sessions, we'll talk in more detail about Spark tomorrow at the Big Fast and Data Furious session. CNTK library Also tomorrow, there is a session on that. And the MXNet deep learning library, we have session tomorrow on that as well. With that, we can switch to Q&A if you have a little bit of time. Yeah, go ahead.
I was just wondering how a Spark server is a Spark on
Spark on
SQL server.
SQL Server? That's a good idea. We should discuss it. At least at the moment, I don't have anything to share about Spark on SQL Server. But we do have Azure Cloud offering that provide fully supported enterprise-ready Spark in the form of the HD Insight clusters.
Hi. Can you hear me? Yes,
Yep.
probably. Is this based on Spark 2.0 or a previous version?
The question is it on the Spark 2.0 or previous version? So the demo that I showed used Spark 1.6.2, but actually this week we are going to release Spark 2.0 in Azure HD Insight service as well. So later this week it will be available.
Okay, and the reason I was mentioning is because we offer a class on Spark 2.0 on Azure, so if anybody here is interested, we have a class that we just tuned for the Spark on Azure and have some brochures, okay?
Oh, fantastic. So if you have interest in Spark 2.0, here's a class for you to come and learn about it. Okay, let's wrap up. I'm still around if you have more questions. Thank you very much for attending.